There are places on this planet where rain is a rare gift, where the ground stays dry for months, where entire cities and farming regions depend on water that simply does not exist nearby. Now imagine that engineers looked at exactly that problem and decided, we will move a lake, not with nature, not with luck, with pipes, pumps, tunnels, concrete, and decades of careful planning. That is what happened in Israel. And today, on Strategic Dynamics Edge, we are going inside one of the most remarkable water engineering projects ever built in the Middle East. A system so large, so carefully designed, and so quietly functional that most people outside the region have never even heard its name. Stay with me, because what you are about to learn will genuinely change how you think about water, infrastructure, and what engineering can accomplish when a nation truly needs it. Before we go any further, if you enjoy deep dive engineering stories, large-scale construction projects, and the hidden systems that keep modern civilization running, this channel is for you. Subscribe to Strategic Dynamics Edge right now and hit the bell icon so you never miss a video like this one. We go deep, we go technical, and we make sure you actually understand what you are looking at. Now, let's get into it. To understand why this project was built, you have to understand the geography. In the north of Israel sits the Sea of Galilee, also called Lake Kinneret, a large freshwater lake surrounded by hills and farmland. It holds a significant portion of the country's naturally available surface water. The problem is its location. It sits in the north. The regions that needed water most urgently, agricultural zones in the center, developing areas to the south, growing cities, were far from this source. Rainfall in those regions was limited. Groundwater resources were under pressure. Demand was increasing year by year as population grew and farming expanded. So planners and engineers began developing a solution at a national scale. According to publicly available historical and engineering records, the concept was to build a water carrier, a connected system of infrastructure that would draw water from the Sea of Galilee, lift it upward against gravity, move it across difficult terrain, store and regulate it, treat it to drinking standards, and then transmit it through a large buried pipeline toward the central and southern parts of the country. This was not a simple canal project. It was a multi-stage hydraulic system, one of the more ambitious water infrastructure undertakings in the region's modern history. Let's walk through how this system is reported to work, stage by stage, because the engineering logic is genuinely worth understanding. The system begins at the lake itself. Water is drawn through intake structures at the shoreline, controlled headworks designed to pull water at a regulated rate from the lake into the system. From there, based on available engineering descriptions, the water enters the first major facility, the Sapir pumping station. This is where the fundamental challenge becomes clear. Water does not flow uphill on its own. The terrain rises sharply above the lake. So powerful pumps at this station push the water with considerable force into large rising pressure mains. Thick steel pipelines anchored to the hillside with concrete supports, anchor blocks, valve chambers, and heavy manifolds built to handle the internal pressure as the water climbs the slope. Every joint in those pipes had to be sealed carefully. Every support structure had to hold under load. The engineering margin for error here is very small. Once the water reaches the upper elevation, it enters what is known as the Jordan Canal, a long, open, concrete-lined channel that follows the natural contours of the Galilean hills. Seen from above, this section resembles a river curving through the landscape. But it is not natural in any way. It is a controlled hydraulic channel with calculated slope angles, sloped concrete walls, a smooth bottom profile, protective fencing, maintenance access roads, side drainage, and inspection points built in at regular intervals. The gradient of this canal had to be engineered with precision. Too steep, and water velocity becomes unmanageable. Too shallow, and the system loses flow efficiency. Every meter of the channel was designed with hydraulic calculations, not approximation. Then the terrain presents a new challenge: valleys. Deep wadis, the dry riverbeds common to this part of the Middle East, cut across the landscape. A canal cannot simply bridge every valley without enormous additional structure. So, the reported engineering solution at several crossing points was the inverted siphon. This is one of the more interesting techniques in the entire project. As the canal approaches a valley, the water enters a concrete inlet chamber, drops into a sealed pressure pipe that descends beneath the valley floor, crosses at the lowest point underground, then rises up the opposite slope and exits through an outlet chamber on the far side. The physics behind this are straightforward. The weight of water descending on one side creates the pressure needed to push it up the other. No additional pumping is required at each crossing, just sealed pipes and the natural properties of pressurized water. This approach allowed the system to cross difficult terrain without constructing a large raised aqueduct at every valley. A brief note here. This video is focused entirely on engineering, construction history, and water infrastructure. The National Water Carrier is a publicly documented project covered in engineering literature and historical records. We are not here to discuss political disputes, territorial questions, or regional conflicts. Strategic Dynamics Edge covers the technical and construction side of major infrastructure projects. That is our focus, and that is where we will stay. After the canal and siphon sections, the water reaches a zone where a regulating reservoir was constructed. According to engineering descriptions of the project, this reservoir, a man-made basin surrounded by compacted earth embankments with slope protection and control structures, serves as a buffer in the system. Water flow through any large network is never perfectly constant. Pumping cycles vary, demand fluctuates, seasonal supply changes. A regulating reservoir absorbs those variations and ensures that what exits on the downstream side is a stable, controlled flow. It functions somewhat like a pressure buffer, smoothing out the irregularities before the water moves to the next stage. Adjacent to this reservoir, the Zalman pumping station lifts the water again, pushing it forward and upward toward the next major obstacle, a hill sitting directly across the route. Rather than routing the system around this high ground, which would have added significant distance and cost, engineers reportedly chose to go through it. A tunnel, known as the Yakuf Tunnel, was cut directly through the rock. This underground passage connects the pumping infrastructure on one side to the Beit Netofa Valley on the other. It is one of the quieter, less visible elements of the entire project, but without it, the route would have required a lengthy detour that would have complicated the whole system. Once the water exits the tunnel and enters the Beit Netofa Valley, it flows into the Beit Netofa Canal, another wide, concrete-lined open channel crossing the valley floor. Like every other canal section in this project, it was designed as a functional hydraulic structure. Culverts manage cross-drainage where smaller watercourses intersect. Service roads allow crews to access any section for inspection or repair. Fencing protects the infrastructure. The entire channel is built so that the water moving through it remains controlled and measurable at every point. The water then arrives at what is arguably the most critical zone in the entire system, the Eshkol Reservoir Complex and the Eshkol Water Filtration Plant. The reservoirs here allow the water to settle after its long journey through pumps, canals, and tunnels. Sediment drops out, flow is stabilized, and then the filtration plant performs the transformation that makes everything else worthwhile. Water drawn from a natural lake, even a relatively clean one, is not immediately suitable for distribution to households, farms, and cities. It carries suspended particles, dissolved organic material, and microorganisms that need to be removed. According to descriptions of the Eshkol facility, the treatment process moves water through mixing basins where coagulant chemicals are added to begin clumping fine particles together, then through flocculation basins where gentle agitation encourages those clusters to grow larger, then through sedimentation zones where the heavier material settles to the bottom, then through filter cells packed with sand and gravel layers that remove remaining particles, and finally through disinfection and into clear wells. Large underground storage chambers before being pumped into the transmission pipeline. This is a standard water treatment sequence, but operating it at this scale, as part of a national system, required significant engineering and operational discipline. From the Eshkol plant, the treated water enters the final and most recognized stage of the carrier, the 108-inch diameter transmission pipeline. That measurement refers to the internal diameter of the pipe, roughly 9 feet across. This large, buried steel pipeline runs across dry terrain, under roads and fields, carrying treated water toward the Yarkon-Negev distribution network that supplies central and southern regions. Along its route, the system includes valve chambers for flow regulation, air release points to manage pressure, washout chambers for maintenance access, cathodic protection systems to prevent underground corrosion of the steel, and service roads at intervals so maintenance crews can reach any section efficiently. When you consider the complete chain, the lake intake, the Sapir pumping station, the rising pressure mains, the Jordan Canal, the inverted siphons, the regulating reservoir, the Zalman pumping station, the Yakuf tunnel, the Beit Netefa canal, the Eshkol reservoirs, the filtration plant, and the 108-inch pipeline, what you have is something that none of those individual components could be on its own. It is a connected national water system, a mechanical hydraulic network designed to move water reliably across terrain that would otherwise make such movement impossible. Based on historical accounts, this system contributed significantly to agricultural development in regions that had previously struggled with water access. It supported urban expansion in drier parts of the country. It gave water planners a degree of supply reliability that had not existed before. And it is widely credited as one of the foundations on which Israel later built its reputation as a leader in water recycling, drip irrigation, and desalination technology. The carrier did not solve every water challenge the country faced, but it changed what was possible, and it did so through engineering rather than luck. What is most impressive about this project, when you look at it carefully, is not any individual structure. It is the integration. The way a pumping station's output feeds into a canal's input. The way a reservoir's buffering capacity enables a filtration plant to operate consistently. The way clean, treated water ends up flowing silently underground toward millions of people who turn on a tap and never think about the chain of engineering that made that moment possible. That invisibility is, in a way, the highest achievement of infrastructure. When it works well enough, people forget it exists entirely. From the air, the national water carrier of Israel does not look like one unified structure. It looks like a scattered collection of canals, pump buildings, reservoirs, and pipelines spread across the landscape. But it is one system. Designed as one system, operated as one system. A water network that engineers planned, calculated, built, and maintained. Not because nature provided it, but because necessity required it, and engineering made it real. If this breakdown gave you a clearer picture of how large-scale water infrastructure actually works behind the scenes, share this video. Send it to someone who has never thought about where their water comes from. Send it to someone who loves engineering and construction. And drop a comment below. I want to know which part of this system surprised you most. Was it the inverted siphons crossing underground? The scale of the 108-inch pipeline? The fact that they tunneled directly through a mountain rather than routing around it? Tell me below. I read every comment. And if you found value in this breakdown, please like the video. It helps this channel reach more people who appreciate this kind of content. Subscribe to Strategic Dynamics Edge if you have not already, and I will see you in the next one.